Record. The other administrative question, do you guys use the recordings? Yeah, okay. So I don't want to do it if no one's using them. Okay, good. Yeah, absolutely then. I apologize for the poor quality of the recordings. There are things that I really wish that I had a grad student minion to make the recordings better, but say let me get something anyway. Okay, so that's the administrative thing. What are we going to do today? Electric field is huge. Electric field is profound. Electric field is what we're going to spend muchly time doing. We didn't do almost any examples at all. So we're going to spend a fair portion of this class dealing with examples of how to use electric field, how to calculate with it, with the one example that we got so far. The other thing is stuff in lab that came out. There were some new misconceptions that I ran into that I haven't maybe asked for, but I also wasn't expecting. Let me see if those hold with the class as a whole and address these, because there's some very important things, important misconceptions that if they exist, I want to make sure to stamp them out. So Google question A, you guys got the Google Forms? And I announced, by the way, that those are now not how I'm tracking grade. Everyone gets free, whatever it is, percent of the participation points. But if you're showing me what you know and don't know, then I tailor the class to whatever I see coming in. But I rage quit the people who are paying zero attention and entering BS just for point grubbing. Drove me so mad. Anyway, yeah, okay, good. Yeah? Okay, Google question one, A. Um, how many pieces, how many chunks do you think scientists, like me, have managed to split electrons into? If you think nobody has ever made an electron, how many pieces is no breaking? One. If you think that we have managed to destroy electrons from the universe by smacking them hard enough in a particle accelerator, maybe looking at supernovas or whatever, say 0 pieces left. If you think that we've been able to split electrons exactly in half, you would say there are 2 pieces. Maybe we could smash electrons infinitely fine, a dust of electron. Take one electron and smack it so hard, you make infinitely many pieces. They would say infinity. So I want you to make a vote between 0 and an infinite number of pieces. How many pieces do you think scientists have managed to smash electron, an electron into? Is an electron destroyable? Is an electron indivisible? Is an electron infinitely indivisible? Oh my goodness, I am so glad we're doing this because half of you are wrong. Okay. So let's talk about this. Electrons are one of the foundational building blocks of the universe. No one has ever managed to destroy one except in a very particular circumstance I'll talk about in half a second. And no one has ever managed to break one. As far as we can tell, electrons are it, baby. No, also, no one has ever measured a radius of them. They appear to be, if you squeeze tighter and tighter and tighter, the electric field gets stronger and stronger the closer you get. You know, the pressure gets higher and higher the more you squeeze it. But no one's ever found a hard shell. No one's ever found a radius beyond which you can't squeeze anymore. You cannot break them. They are unbreakable, unbreakable by any particle physics experiment or even any supernova that we've observed with higher energies than we'll ever be able to make here on Earth. No gamma ray burst, no black hole merger, no particle accelerator has ever seen a split electron. Protons and neutrons you can split. Protons and neutrons you can split. Protons and neutrons are made of things called quarks. Quarks you've probably never heard of. Well, who's heard of quarks before? Oh, okay. So you've heard of them at least. Who's done chemistry with quarks? Who's done quarks in chemistry and used them? That's right. They're utterly useless from a non-physicist perspective, because quarks have no interactions with the electrons, effectively with the electrons. They do not alter the chemical properties of atoms and molecules at all. If you want to understand the way the world works, sure, quarks are absolutely vital. As far as anyone knows, quarks are point indivisible particles. And the protons and neutrons are smashable into pieces, the pieces being the quarks. But and there's neat stuff about that, real neat stuff about that, which we cannot possibly have time to cover. Ask me in office hours. Yeah, protons and neutrons, not fundamental, not indivisible, but electrons, oh boy, baby, are they ever. Not breakable. Okay. There's a follow-up to that. I did mention that there is one special way to destroy them. Who's heard of antimatter? Sci-fi or real? They're real. Antimatter is real. You are not made of antimatter particles at all. At all. Antimatter is not a constituent of the Earth and everything around you. Our entire galaxy, it seems, does not have antimatter in it, except for a teensy fraction, which we make here in labs on Earth. You can manufacture antimatter. It takes a redonkulous amount of energy, and it disappears real fast. And where it disappears is, if antimatter smashes into regular matter, it turns back into pure energy, the energy used to create it. So, antimatter electrons exist. They're called positrons. They're positively charged. They have exactly the same mass, exactly the same every other property. You can do chemistry with them, which is really freaking hard because you have to do chemistry in an utter vacuum without letting them smack into anything else. But you can put an antimatter atom together, observe its properties, and it's the same as regular matter atoms. So antimatter positron has positive charge and is in every other way electrically identical is in every other way that we can observe identical to electrons. But you're not made of them. We don't see them at all, ever, even a little bit here. And there is a very important thing. Positrons have positive charge, duh. Electrons have negative charge, duh, right? When they come together, plus and minus can cancel, releasing zero total charge. Note that we have not changed the absolute value, the net, not absolute value, the net charge of the world. If you've got 5 negatives and 1 positive, that is to say 5 electrons and 1 positron, your total charge is -4 units. If you then allow one of those positrons to destroy one of those electrons, then you're left with 4 electrons and a ton of energy. Still -4 units. We could do cool stuff in physics labs these days. In the last century, we've discovered some really freaking amazing stuff that I just don't have time to tell you. But what? But, and this is a big but, we have never, ever, ever observed charge being created or destroyed individually. The total amount of charge of the universe really does appear to be completely fixed. As far as one can tell, the total amount of charge, electrons and protons combined, like, not positrons. Positrons are so stupidly rare, you don't even need to think about them or know about them, other than me telling you right now. Total number of protons plus the total number of electrons really does seem to be 0. Balanced. Total charge is balanced. Okay. Google Quested B. Let me check other misconceptions. I've got an ion, I don't know, helium +1. Helium +1. There is an ionized helium. Helium, as you may remember, is element number 2, atomic number 2. I'm curious if you could tell me, how many protons does it have? Google Question B. How many electrons does it have? And how many positrons does it have? Yeah, yeah, yeah. In the helium +1 ion. Has everyone taken Gen Chem at all ever, right? Yeah? All your majors require at least a smidgen of chem? Periodic table. It is element 2. Hydrogen, then helium. Okay. Google Question B. B, C, and D. How many? What I asked? Protons, electrons, protons in helium ion? How many electrons do you think in helium ion? +1 helium ion. And how many, the symbol for a positron is an E plus. Just say a number. Real fast, chop chop. I don't want to spend all day on the misconceptions. I do want to iron them out. But positrons are antimatter electrons. They have positive charge. They don't make up regular matter at all. You have 0 positrons in your body right now, I promise. Maybe not 0. There is 1 isotope. They're not a major constituent of matter at all. I'm asking helium +1 ion. If I take a helium and knock 1 electron off, helium is element 2. How many protons are there in helium-1? Helium +1. How many electrons do you think there are in helium +1? How many positrons do you think there are in helium +1? And I'm going to have you turn to your neighbor and argue for your point, your perspective. I have a fair number of people not actually reading the question, by the way, or listening to what I just said, but let's take it one step at a time. Go on, talk to each other, check each other, argue about it, real fast. I'm grading. Oh my God. Okay. Yes. Super important. More than half of you. Okay. What was the last thing I just said about how common positrons are? Did I say that you have any of them probably in your body? Do you think that there are any helium atoms inside you at all? Maybe? There's nothing? I mean, if it is a noble gas, probably not part of biology much. Well, you could rely on this. I also said that it does not make, positrons do not make up the world around us at all for realsies, except in physics labs doing particle physics where we're experimenting with the boundaries of nature. Okay. Half of the class said that there are 1 or 2 positrons inside an ionized helium. That's not the case. Let me emphasize this. There is a thing called a positron. It does exist. It is part of the universe. It is so insanely rare that it's not part of the Earth. There are probably half a dozen of them on the planet at any given time, and those are because we just made them in a lab. 0 positrons. How many protons are there in atomic number dose? 2. That's the meaning of being helium. So there are 2 protons in helium. That one, 75% correct. Electrons. If I've got 2 protons and a total of 1 unit of excess charge, positive unit of charge, how many negatives must there be? 1. Exactly. 2 plus -1 is the positive 1 left. Okay, I like it. I'll take it. Hopefully that sticks. And that tells me I need to put some questions on the test that haven't been there before. So show of hands again, who has never had Gen Chem? Everyone has been required to take Gen Chem. So you've all learned about the periodic table and all that? Maybe the people who are online are the ones missing this. I don't know. Okay. If you have a question about protons, electrons, and positrons, please post it. I want to know. Juju question E, we're just going to do a Couple more of these. What was the other thing that I saw screwed up? Just a sense of scale, rough order of magnitude sense of scale. Three questions. EFG, how big is a proton compared to an electron? Roughly. This I'm going to grade with extraordinary wide margins. How many times bigger? I hope you all know that protons are bigger. How many times? What is the ratio? And I should be precise, more massive is a proton. Don't look it up, by the way. I'm looking for your gut intuition to see if you got a feeling for this stuff. AF, how many? How many protons do you think are in just any old metal that you encounter? Let's say copper. How many protons in one copper atom? G. How do I want to word this? How do I want to word this? How do I want to word this? Okay. When I'm talking about roughly what I want is powers of 10, let's say. If you think that an atom is 6, 7 times proton is 6, 7 times more massive, that's rounds to 10. If you think it's 20 times as big as electron, that rounds to 10. 30 rounds to 10. If you think it's 50 times bigger, round to 100. If you think it's 354 times bigger, that rounds to 100. If you think it's 1,965,000, that rounds to 1 million. Give me the power of 10 closest for each of these. The ratio, how many times more massive is the proton than the electron? If you know exactly this, screw it. Screw it. Give me the power of 10 closest to the number of protons in a copper atom. Round everything to powers of 10 so that I can read and grade this real fast. And then here's the challenge. How big is a whole atom compared to a single electron? Again, I want you to round the hell out of it. I want to get a feeling for if you have a feeling what just how big stuff actually is. Oh, try a number. I got a bunch of people saying a lot. Come on. Give it a shot. Again, I'm asking how much bigger is one proton than one electron? Flay how many protons in one copper atom? One copper atom. And roughly how much bigger is the whole atom than each individual electron? Ten to the 128th power. One with 128 zeros after it. There aren't 1 to the 128 particles in the known universe. There's something like 10 to the 57, I think, last I checked. I've got a bad memory. 10 to the 57 particles in the entire universe. Now that's just a count, not a mass ratio. But still, if you guessed bigger than a Google, you guys know the word Google, not the company? Googol, 10 to the 100 power. If you guessed more than a Google, you're wrong. Say that. Okay, has everyone had a chance to vote? Get a feeling for this. Get a feeling for this. No, I'm not going to test you on these exact numbers, but the more you have some kind of intuition, the more you can pick out BS from answers, the more you can recognize, oh, that can't possibly be it. The precise number, screw it. The rough number is about 2,000 times more massive. So an electron is about 1/2000th the mass of a proton. All the electrons in an atom added up together do not equal the mass of one proton or neutron. Hey, which is stronger electrically, one proton or one neutron? Let me put this to the test. Google form H, which has more electrical effect on stuff? One proton or one electron? If I hold up a proton and I hold up an electron and I don't do the banana dance, pen, apple, apple, pen dance, then which will pull or push on something harder? Okay, most people are saying the electron. I have given perhaps a misconception when I say that a lot of stuff that we do is the story of electrons. Electrons are the actors in our play, but not because they're more common, not because they're more powerful, but because they flow easier. Electrons are exactly as powerful as protons. One electron does exactly the same electrical oomph as one proton. Opposite direction, opposite sign, sure, but same electrical push or pull. So, well, here, I was leading up to this, 2,000 times as massive. And there are something like, well, the correct answer is like 30 for copper. I don't remember the periodic table perfectly. So what, 30 times 1,000 is what? 30,000 times more massive? Hopefully your answer for G was the product of those two, yeah, right? One proton times how many protons is how much the atom is, roughly? I'm ignoring the existence of neutrons. Okay, so something like 30,000, 60,000 times heavier. That's why we care about electrons more. You get the same force on an electron as a proton, but the protons are bound inside the atom. The protons are stuck together with a very strong nuclear force. The protons are not free to move because their atom is 100, 300, 600,000 times more massive. Apply the same force when the mass is bigger, you get less acceleration. F equals ma, baby. So I want to emphasize this. If I have 1 coulomb of electrons, or maybe I should say negative 1 coulomb, and I have 1 coulomb of protons, 1 coulomb is 1 coulomb. 1 coulomb has the exact same electrical effect as 1 coulomb of electrons, or the exact same strength as negative 1 coulomb. 6.25 times 10 to the 18 electrons has the same push or pull. Now, if I take 1 coulomb of protons, sit them somewhere, and take nearby 1 coulomb of electrons somewhere, first off, that's enough energy to destroy a large fraction of the planet. We'll calculate that in a moment. Maybe not today. If I take 2 balls of 1 coulomb of protons, 1 coulomb of electrons, which is going to accelerate faster? If I let them go, just hold up to 1 coulomb and negative 1 coulomb and let them go, what's going to happen? Google form I, tell me what you think would happen. Are the electrons going to accelerate faster, or are the protons going to accelerate faster, or are they going to accelerate at the same rate? I will give you a hint that the force that they exert on each other, held by Newton's third law, the force has to be exactly equal. Does that mean that they're going to accelerate the same, or that one is going to beat the other? Okay. This is absolutely vital then. No. Three-quarters of you know. What did I just say when I was standing over here? What did I just say a minute ago? Rest of atom big, electron small. Force same. What did we spend half a year doing last semester? PHMA. If the forces are equal and the masses aren't, which one moves? The electrons. The electrons. The electrons are a million as massive. They will accelerate a million times faster than the protons because they get the same force and have less mass. Write this down. Take this down as a note. I am inspired. This is going on your next midterm. A question to this effect. I have a proton. I have an electron. I let them go near each other. Which experiences the greater force? Equal. Which experiences the greater acceleration? Electron. Hey, don't forget FMA. I'm giving you guys extra homework, okay? I want all of you to go out and, as hard as you can, kick Dwayne the Rock Johnson. And then, poor guy, and then as hard as you can, go kick a baby. Okay? Which one is going flying further? Same force, smaller mass, bigger acceleration. Maybe we shouldn't do that as homework. No, no. Upon my learned consideration, I cancel that as a homework. Don't sue me, people. I don't have any money. I just bought a house. All right. So Yami asked for me to repeat, and I will gladly repeat. Super important here. F equals ma says equal forces, unequal masses have unequal accelerations. One electron compared to the honking rest of the atom, one electron is itsy bitsy teeny weeny. One electron versus one proton is itsy bitsy teeny weeny. If I take the same number of electrons and the same number of protons, they have exactly the same electrical strength. Of course, one will push where the other one pulls, but the magnitude of their pushes and pulls are equal. A test question I may give is, hold up 2 nanocoulombs worth of electrons and 3 nanocoulombs worth of protons. Doesn't matter. No, I'll say it equal. I'll say it equal. Make it even more clear. 2 nanocoulombs worth of protons, negative 2 nanocoulombs worth of electrons. Okay? Which experiences the bigger force? Answer is neither. Their electrical effect is exactly the same. Which would experience the bigger acceleration? The electrons by a huge margin. Hell, let's calculate it. Let's calculate it. Yes, thank you, Yami, for raising the question. Let's calculate, suppose, what the hell, let's do exactly that example. Yeah, first. The force is always going to be the same if we're talking Newton's third law that makes forces that A exerts on B equal to the force of B on A. The only way you could have the electrons accelerate equally to the protons is if you had 2,000 times as many electrons as protons. Then the force would be equal, but the masses would also be equal. Then they'd accelerate the same way. I wouldn't give that to you. That's too tricky to ask on a test. Okay, let's calculate it. I hold up, I like simple numbers, 1 nanocoulomb worth of protons and 1 nanocoulomb worth of electrons. As it happens, this is still a freaking lot of energy. I hold them up 1 centimeter apart. How many meters is that? 10 to the minus 2? How many cents are there in a dollar? 100, yeah, 1/100th of a meter. All right, so I'm going to hold 1 nanocoulomb and -1 nanocoulomb of charge next to each other and let them go. I will give you the mass. I will give you the charge number and the K constant. Your first task is let Q. Let's focus on the electrons. Let's focus on the -1 nanocoulombs. The way to do any of these problems, here's how I want you to approach any of these problems. Here is something that I might give on the test. Find the force on the -1 nanocoulomb of electrons, that left particle. If you actually stick -1 nanocoulombs worth of charge all together at a single point, it will blow up big time. Maybe not the big fraction of the planet, but still big. Okay. So where are we? What are we doing? Oh, for God's sake. Here's how I want you to do this. The law that we learned yesterday, class, is force equals a charge which feels times the electric field that is caused by. So if you want to find the force on the electrons, which charge do I use here? The electrons. If I want to find the force caused by the protons, what numbers do I use for the electric field? The protons. Now I let both of them be equal magnitude as it happens. The number will be the same either way here. Screw it. I want you to be able to identify that the Q is the thing that is feeling and the E is caused by the thing that is causing the force. Okay, so in this case, what I'm going to say is 1 nanocoulomb. Please note, I am going to drop the plus minus sign much of the time. Let me think about this. What does a plus or minus force mean? Left or right, yeah? There is a way to do this logically, but you're going to have to track 3 different things with signs, and one of them is freaking hard. When you are doing force and electric field, I don't want you to plug in negative numbers for negative charge. I want you to remember whether you have negative or positive charge and reason about, does this push or pull? I mean, sanity here. Which direction do the protons pull the electrons, left or right? You got an attractive force, opposites attract. Which direction are the electrons pulled? Google Form J. I set up some protons. I set up some electrons. They attract each other. Which direction are the electrons pulled? Left or right? Google question J. Look at the diagram. Okay. I think that too many of you are still thinking about what the electrons do. If the electrons are sitting over here, they are the thing which is pushed or pulled. That's what I'm talking about right now. If we're focusing on the electrons, think about being the electrons. Am I pushed or pulled by that? If I am pulled by that, I must also pull that in turn, Newton's third law. Ignore that! That's a force that I exert. I don't feel the forces that I exert. I only feel the forces exerted on me. So if this sucker is attracted this way, which direction am I pointing when I say attracted this way? I am pointing right. This is the right direction. So the correct answer here is the electrons are attracted right. Google form K. What direction is the force on the protons real fast? We're going to do numbers again in a second. What direction are the protons pushed or pulled? Oh, thank God. Okay. Down is incorrect. Hey, by the way, I do want to point out, yeah, these things have mass, therefore they have a weight force. They are so itsy bitsy teeny weeny yellow polka dot between. No, they are so itsy bitsy teeny weeny. Gravitational force is utterly swamped by electrical forces. If I've got a charge and I've got another charge, they don't care about gravity. They are pushing and pulling on each other. Big time. Okay, the correct answer is if the electrons are pulling the protons, I imagine being the protons, I imagine being pulled. Which way am I being pulled? Well, which way is my finger going? I'm pulled left. Many more people got that one right. Correct, I should say. Some people got that right, which is wrong. Okay, so here's again how I want you to do this. As I was emphasizing, we use the absolute value of the charges when we are finding the number for the force. We use common sense, push or pulled left or right. You have to look at the picture to figure out whether use the common sense to say, is this pulled this, that, or the other direction? Is this pushed that, this, or the other direction to figure out positive or negative force? Q, 1 nanocoulomb. Electric field, anyone remember the formula? K, 9 times 10 to the 9. Q, 1 nano is 10 to the minus 9. Remember, you need to know those, though. You need to know down through pico. Over what squared? R squared. Oh, if I'm actually writing numbers, instead of nanocoulombs, I need to express in coulombs. So I've written Q times E, the magnitudes anyway. Okay, we got some real grueling mathematics here. Let's see if we can do this. What's 10 to the 9 times 10 to the minus 9? 10 to the 0, what's 10 to the 0? So 10 to the 9 and 10 to the minus 9 cancel. This is also called, what is 1/billionth of 1 billion? Okay, so upstairs is just 9. What's 10 to the negative 2 squared? Do you guys know? Minus 4? 10 to the minus 4, right? Okay, what's 1 over 10 to the minus 4? What happens if I've got a negative power downstairs? Okay, we're going to review this real fast. Powers! When you multiply them, they add. Sidebar, muy importante skill. Yes, you can use your calculators for a lot, but if you have some... Okay, real fast. Hey, make your math better, especially you future doctors. You actually need to know this, at the very least for the MCAT. Anything to the 0 power is 1. If I multiply exponents, that's the same thing. If I multiply 10 to the something by 10 to the something else, I add the exponents. A negative exponent is the same thing as 1 over. Therefore, 1 over a negative exponent would be 10 to the something. 1 over 10 to the minus x is 10 to the x. I encourage you, if you don't know this, practice this, learn this, think about this, go Khan Academy something. God, I hate Khan Academy for most uses, but in this case, it's important. So all this stuff, 9 times 10 to the 9 times 10 to the minus 9, that's 9 over 10 to the minus 4, which is to say 10 to the 4. This becomes 9 times 10 to the 4. What are the units? This is the electric field, by the way. What are the units of the electric field? I will remind you that force is newtons, charge is coulombs. What must the unit of the electric field be? Do you see I've written force equals charge times field? What's field? Google form. Google form L. Force equals charge times field. What must the units for field be, logically? I should point out electric field. I'm not talking about magnetism. Don't tell me Teslas. One second. People are saying volts per meter are correct, but that's not how I want you to think about it right now. Volts per meter is equivalent to this answer. Okay, that's enough correct answers. What do I need to multiply C by to get N? I think I need to multiply it by N divided by C. Well, I would like you to write, for now, the units for electric field are newtons per coulomb. Later, we will find out that this is equivalent to volts per meter. We're not there yet. So, electric field, 9 times 10 to the 4 newtons per coulomb times charge, 10 to the minus 9 coulombs equals what? How much force? Is that big? Is that a lot of force? What do you think? Well, let's find the acceleration using F equals ma. The mass of one electron is roughly 0.29 zeros and a 1 kilograms. So if I've got about 1 billion of them, that would mean in this case the mass of this object is about 10 to the minus, oh god, what did I just say? 10 to the minus 30, 10 to the positive 9 would be 10 to the negative 21, right? Yeah. Okay, so in this case, this many electrons, I will just tell you, have mass approximately equal to 10 to the minus 21 kilograms. Find the acceleration. Google form M. Find the acceleration. I'm rounding the hell out of that, by the way. The mass of an electron is not exactly 10 to the minus 30. And the mass of this many nanocoulombs would not actually be exactly that. This is M, not N, not L. Follow instructions. Oh my God. When you're doing division, you need to use order of operations. You cannot divide without parentheses when you've got 10 to the something. Oh, for God's sake, get back. Hmm. What's 1 divided by 100? 1 divided by 100. 1/100th, yeah? Type this into your calculator exactly as shown. 1 division 1e2. Real fast. Wait, you guys aren't typing it that way. Never mind. You don't know about the E key. Most of you, many of you. There. That's how you guys do exponents, right? Most people that I've seen in tutoring. Yeah? Do you guys do it this way? Great. Type this straight into your calculator. The answer had better damn well be 0.01, right? 1/100th? What do you get? No, you don't. No, you shouldn't. Your calculators interpret it correctly? Yeah, you put parentheses because you know to put parentheses. If you type it in as shown, what do you guys get? 100. Is 100 equal to 0.01? No, 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 no. Watch out. Why does this happen? Because PEMDAS says multiplication and division happen left to right, and multiplication is not more important than division. So it will do the division first, then the multiplication. The exponentiation is separately done, then multiply it by. What's 1 divided by 1? 1. What's 1 divided by 1 times 100? Turns into 100. So my point is, I got a bunch of people get the wrong answer here because they are typing in what? 9 times 10 to the negative 5 divided by 10, 1 times 10 to the negative 21. Is that what you guys are typing when you get a positive number? When you're getting a negative exponent? If you got something like 10 to the minus 26, is this what you're typing? Maybe it's all the online people. You guys are getting this right? Okay. So here's the dealio. If you are dividing by something with multiplication in it, you have to put parentheses around the downstairs for it all to be treated as doing the downstairs together. The correct answer is the acceleration is on the order of magnitude of 9 times 10 to the, not 26, 16, positive 16 meters per second squared. Earth only accelerates things at 9.8. This accelerates things at 9 times 10 to the 16. It accelerates at what is that? Is that 1 quadrillion? No, that's 1 trillion times faster than Earth's gravitational field would. Oh my gods! These electrons be trucking. You see that? The protons, what force would they have? What magnitude force would they have? Bigger or smaller? Go back and look at the calculation. If I plug in instead of the charge of the electrons, I plug in the charge of the protons here, and instead of the charge of the protons, I plug in the charge of the electrons here. What happens if I swap those two numbers? Which is bigger, multiplying 10 to the negative 9 by 10 to the negative 9? Or multiplying 10 to the negative 9 by 10 to the negative 9? It's the same number. Even if the charge has had different magnitudes, 1 nanocoulomb, 5 nanocoulombs, what's the difference between 1 times 5 versus 5 times 1? The force is the same either way. Okay, so the force is the same. Now I'm going to tell you 1 nanocoulomb worth strictly of protons would have 1,000 times as much mass. Yes, roughly, sort of. It's actually 2,000, but screw it. So now I'm going to say, okay, force is still, what did we just say? 9 times 10 to the negative 5 newtons. Mass of protons is, instead of 10 to the minus 21, 1,000 times that, 10 to the minus 17. Great. Find for me Google question N. Google question N. Find acceleration of the protons. Do you guys know when I say P plus, that means proton? P plus means proton. If you don't know that, now you do. And watch your parentheses. Oh, for God's sake, I can't subtract. It's not 21 minus 3 is not 17. Oh, for God's sake. Sorry. Just a second. This hurts my soul to say this. This hurts my soul to have it on the board. Don't tell my dissertation advisor that I did that. Try that again. I was thinking, what the hell are you people doing? And it's actually, what the hell am I doing? Billion, by the way, is 10 to the 9. This is not 10 to the 9. Oh. If you take 9 and divide it by 1, does it make sense to come up with 5.4? Sanity, sanity check your answers here. What is the formula? Force equals mass times acceleration. Force divided by mass. 9 times 10 to the minus 5 divided by 10 to the minus 18. There's no 5.4. How could there be a 5.4? There's no 5.4. Okay, compare this. Which is accelerating faster? Jazz hands. By a factor of 1,000 times faster. Is this a realistic real-world scenario? Oh my God, no. This amount of acceleration, 0 to the speed of light in nanoseconds? No, 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 just no. But the important point here that I wish to make, that I will test you on, forces are identical. It doesn't matter which order you multiply two numbers in, but the acceleration depends on the mass. Big mass, small acceleration. And we go back to the very beginning of lecture. Why is it that we care more about the electrons than the protons? The protons are big and donkey. They accelerate less. They move less. They're heavy. They're stuck inside a nucleus with the rest of an atom around them. It's huge compared to the electrons. I apply equal forces because the charge of a proton and the charge of an electron have equal electrical effects. If I apply equal forces, pew, the electrons spit out of there, and I mean the rest of the atom isn't going anywhere effectively. Okay, turn to your neighbor and express this in your own words. Why do we care about the electrons in electrostatics and current electricity, and why am I not talking about the proton so much? Questions? Okay, next thing I wish to bring up. How did I get there? I got electrons on the left, I got protons on the right. I have separated them somehow. Magically, I've ripped that nanocoulomb apart from that -1 nanocoulomb. How did I do that? Did the electrons move left? Did the protons move right? What? I applied a force to them to pull them apart. Which one moved? The electrons! Why? Because they're so much lighter. If you apply an equal force, I'm not going to tell you the kind of force I used. Maybe I used magical force. I'm actually a wizard in disguise, sent to terrorize you to keep the muggles in their place. Yeah? So, whatever force you use, you apply a force to the electrons and the protons. It's the electrons that are flying. Same force, smaller mass, bigger acceleration. Let me test this. People said it verbally out loud, but I can't hear 40 people at once. Polarization. I have a metal ball with charge 3 microcoulombs plus 3 microcoulombs. I want to emphasize that the 3 is a positive number. Have I How did I get here? What are we on? OP? P. What we call onto the ball or away from the ball? So the legal answers here, make it easy for me to grade, please, is for O, you can vote electrons or protons. For P, you can vote onto or off. Off of if you're feeling fancy. Please reflect on what we've been doing all this time, the lessons that we just learned, hopefully. If I've got a metal ball with 3 microcoulombs of charge, okay, look, you really drive me crazy sometimes, some of you, well, just a couple of you. When I write a letter next to a question, what's this letter mean? Does this letter mean answer everything in question Google Form O? Does this mean answer everything in the world in Google Form P? No, I asked 2 questions. I have 2 Google spots. That's what these letters means if you haven't gotten on to this. I got people answering 3 things in 1 letter. Okay, let's see. Great! All but 1 person got that electrons are the things that moved onto this, off of this. We have subtracted negativity and we are left with positivity. What happens if you've got a party and then you remove all the stupid, boring people? You're left with a more rockin' party, right? If you take all the bad things away, you're left with good. Not that that ever happens because everything is actually bad in real life, but yeah. Great, let's do another problem here. Here's a homework problem that I was just asked about. Hey, what is it? I'm going to give you coordinates and charges. I put 3 microcoulombs at xy equals 0, 0 centimeters. And that looks like a plus. And I put -2, what the hell, microcoulombs at xy equals 5 centimeters, 0. I will remind you that these coordinate pairs mean first the x direction, then the y direction. Find the force exactly as I showed you. First think about how strong, and then reason about, is this pushed or pulled, attracted or repelled? Direction. On the 3 microcoulomb charge. And I want you to split this out. Oh my God, split this out. Q magnitude. Q Oh, for God's sake, the letter after Q is R. Talk about silliness. Please pay attention to the units, by the way. Microcoulombs, centimeters. I'm only ever going to give you things on axes, by the way. If you see something where I've got multiple directions at once, yell at me and I'll give you free credit for that question and take it off, or I'll make it extra credit or something. That involves trigonometry, which is beyond the scope of this class. Like on the homeworks or whatever. I check, but sometimes I don't check carefully enough. Six times 9 is 54. 54 divided by 25 is 202. 2, so that's micro is negative 12. Negative 12, for God's sake, negative 12 plus 9 is negative 3 upstairs. Negative 3 upstairs. What have I got downstairs? What did I freaking just say? Negative 12 plus 9, negative 3 over negative 4 is plus 1. So times 10 to the freaking fracken. So I expect 20. Use the formula, Luke. Find the field. Find the force. Question me. What do you want to find? What do you want to find? This is the force of electricity. F equals ma is Newton's law. It tells you what the forces do. Oh, there are definitely two different formulas. Look, I'm 6 feet tall and I weigh 130 pounds. Those are both true statements about me, but they're referring to different things. Newton's second law refers to how force causes motion. This is a particular kind of force. The correct answer for O and P were electrons off, by the way. Do this the exact same way I just demonstrated. I will remind you of the formulas, by the way. Electric field. And then to find the force, multiply it by the test charge, whatever is feeling. Oh, questions. I like questions. Oh, already answered. And I should remind you. Excuse me. Is the formula that I just wrote Q times Q? Did I just write Q times Q? The answer's not 6. Don't just multiply 2 times 3. That's silliness. Use the formula, Luke. Okay, what's each letter mean? K is a constant, 9 billion. Q, which Q? Which Q does it make sense to be? The big Q in electric field is the cause of the force. Which one is causing the force in this question? The -2 microcoulombs. Now remember what I said. Determine the direction separately. Micro is -6. If you don't know that, you need to know that. What's R? It's not 5. 0.05, yeah, or 5 times 10 to the -2. Okay, what's that? 18 over 25 is, oh crap. 18 over 25 is 7.2? 0.72. 0.72. Are you quite sure of that? I think the electric field should be something like 7 point. Yeah, careful. R squared. What is it? 0.72? No, 7 times 10 to the what? Okay, the magnitude of the electric field, 7.2, 10 to the 6 newtons per coulomb. Who got that far? Good. Plug in, plug in, plug in. Don't forget the square. Okay, now to find the force. Which Q is little q? What does it make sense to plug in? What am I asking if I want the force on the 3 microcoulomb? That is the thing that I'm asking. That is the test charge. That is the object under study. That is lowercase q. That is not scrolling. Yep. Which if we're talking about, you know, microscopic stuff is a ridiculous amount of force. Because I just asked Q is the magnitude. Now let's reason about the direction. The force on which one? The positive or the negative? On the 3 microcoulomb charge? Is the 3 microcoulomb on the right or the left in the diagram? I mean, look at the coordinates. 3 microcoulomb at the origin. So I ask myself, if red is attracted to blue, which direction does attraction look like? That's right. So I would answer this as 21.6 newtons per 21.6 newtons to the right in Q and R. We're out of time. I love you all. Have a good day.